All right, welcome everyone. I am Nat Klein. I'm going to be your instructor for tonight. I just want to start by saying, thank you to everyone for being here. I applaud you for, I know a lot of you probably have just had a full day at work. And so it's a lot to, log on to a workshop and really focus yourself for 2.5 hours on some pretty challenging topics. So I applaud you for being here. And yeah, welcome. This is JavaScript, the hard parts. Today, we're going to be covering closure, a very, very interesting topic, very powerful in JavaScript, allows us to do a lot of cool things. And so today we're going to go take a deep dive under the hood, and we're going to learn more about closure. Now, I would love to hear from some of you. We don't have time tonight to have everyone provide their intro, so I'm just going to do a few of you. If anyone would like to introduce themselves, this is going to be your name, where you're currently tuning in from, how many how many Codesmith workshops you've attended, as well as a JavaScript resource that you would like to share with the group. You can go ahead and raise that virtual hand right now. If you go to the bottom of Zoom, it's not even showing up for me, but you can raise your virtual hand. All right, Robbie?
Yeah, hi. I'm Robbie Gottlieb. I'm tuning in from formerly sunny Brooklyn, New York. It's nighttime now, and I think this is my fourth or fifth, my fifth JavaScript Codesmith workshop.
Awesome, very cool. Have you been to a closure one before, or is this the first closure topic?
This is the first closure one.
Awesome. Well, I hope that you get a lot out of it. And Robbie, do you have a JavaScript resource that's been helpful to you?
Yeah, so definitely CSX is the one I've used the most, which I found it unbelievably helpful. And then Google is my second. When I'm struggling on CSX, I definitely turn to Google.
Awesome. Very engineer-like. Robbie knows. Googling of success as an engineer. Well, welcome, Robbie. Thank you for sharing that with us. I see two other hands up, Harry and Daniel, although you have your cameras off, so I'm not sure if you would like to introduce yourself. How about let's go to Anna. Anna, could you share with us where you're tuning in from, how many workshops you've been to, and a JavaScript resource that you found helpful?
Okay, hi there. I'm Anna, and I am from Northern California, and I may have attended 7 Codesmith workshops, not entirely sure. My favorite resources are CSX. Codecademy was a great supplement for CSX, and Traversing Media has a really great way of teaching, and REPL is really helpful in trying to edit through my own code.
Awesome. Well, thank you, Anna. So 7. Let's see if anyone has Anna beat Augustine.
Hello, my name is Augustine. I am from Los Angeles, California. This is probably my 3rd workshop, I believe. But I also was in JSB as well as CS Prep. My CS Prep class actually ended, I think, like 3 or 4 weeks ago. So just prepping for my technical actually coming up next week. Favorite resources, CSX has been great. MDN is my quick go-to if I'm looking up specific, methods or whatever. And then for daily practice, I really like Code Wars, even though it's a little intense. So Edibit is a bit of an easier version of Code Wars, but I've been using both of those as well.
All right, awesome. Very cool. Well, good luck on your technical interview coming up next week. Let's see, we have time for one more. Anyone else want to introduce themselves? Yeah, Eli or Ellie?
Yeah, you got it right the second time. Hey all, my name's Ellie. I believe this is my 3rd Codesmith class. Really excited to be here. I recently moved from Northern California down to Southern California. And yeah, I don't really have any previous experience in this, but I did dabble in JavaScript when I was in high school, so I think I'm excited to get back into it. So yeah, thank you.
All right, well, awesome, Ellie. I am also from California. I don't know if I said that in my intro. I'm from Agora, kind of the valley outside of LA. You might consider it the valley, depending on, you know, if you're from the valley or not from the valley, but it's right there. Cool, a lot of California people. Well, thank you to everyone who just introduced yourself. I like to kind of get an idea of who's here tonight, what we're working with. All right, awesome. Well, tonight, I am going to, throughout the lecture, throughout the diagramming, we're going to be doing some live Codesmith diagramming. So I'm going to ask some of you to help me out with that. And if you have, especially if you've been to a hard parts before for these first few code snippets that we're going to diagram out, and you've done the diagram before, like there's no better way to practice than to do it in front of people. And also, you know, as I said, we really focus on very kind of specific technical communication. So if I correct what you're saying, it's not because I'm trying to like make you feel bad or be like, you did this wrong. I was gonna say it's not because I'm being nitpicky, but I am being nitpicky, but because it's just so important to us to have that good technical communication. So just be prepared for that. I'm here to try to, you know, help you to be better, but that's what's coming. Also, periodically throughout the lecture, I'm going to ask for thumbs. And this is very common at Codesmith. This is to get a gauge of understanding. So I'm looking at all of you on the Zoom screen. I can see, you know, basically where people are. If you've got it, it totally makes sense. Give me a thumbs up. If you have maybe a question or you need some clarification, I can give me one of these sideways ones. If I've totally lost you, you know, you can give me one of these. And at that point, when I ask for thumbs, feel free to raise that hand, and I'll take some questions. I will wait until kind of these periodic breaks to take questions, just so we don't, you know, disrupt the flow of everyone else following through. But I will get to them. So, all right, cool. Now that we have done that, we can jump into the fun stuff. We can jump into the code. So we are here tonight to learn about Clojure, and we are going to get to Clojure. We're going to diagram some examples of Clojure. We're going to look at sort of how it works under the hood and the advantages that it gives us. But first, we are going to start by developing kind of this mental model of how we think about our JavaScript code, how we think about how the interpreter, this mechanism in our browser that reads our code the same way that humans, you know, read a book. It reads from left to right and down if you're reading in English. How the interpreter, how JavaScript reads through our code, stores some data, and then does some things with that data. That's basically what the internet is some data, like some strings, some names, some numbers, maybe some of those things packaged together. Those exist, and then we do something with that data. Maybe we move it around, you know, send it wherever. But we're going to get this mental model of how JavaScript runs through our code. And then, yes, we will get to Clojure. Clojure is one of the most esoteric topics of JavaScript concepts. You might be surprised that many senior engineers who have been working with JavaScript for years and building applications don't have a really fundamental understanding of how Clojure works under the hood, how it's really working. So we're going to try to kind of start with these building blocks, to start with this deep understanding, so that when you build upon it, you know, there aren't any gaps. So that's the goal of these hard part sessions. Clojure also enables us powerful pro level functions like once and memoize, very powerful functions that allow us to kind of keep an important principle of JavaScript that we always try to follow. It's the dry principle. When we make our code dry, does anyone want to let everyone else know, what does dry stand for? Why do we want to keep Carson, what does dry stand for?
Do not repeat yourself.
Yeah, don't repeat yourself. We as coders, we are lazy. No, we're not lazy, but we don't want to write repetitive code. If we have like Some code, we only want to write it once. And so closure is one of the tools in JavaScript, one of the pieces that allows us to do that. Closure is powering many popular and useful JavaScript design patterns, including the module pattern, something that we learn about in our design patterns lecture in the Codesmith Immersive. Closure allows us to build iterators and maintain state in an asynchronous world. We have a whole hard parts on async. Really recommend you attend that one. That one's very interesting, goes into a complex topic. So those are the advantages of closure. But as I said, first we need to develop this mental model of JavaScript. So let's start with the most basic pieces of JavaScript. As I said, when JavaScript, we send our code, we send these lines of code and we send it to the computer and we say run JavaScript, or the JavaScript interpreter is going to run through our code line by line. Similar to how if you were like reading a book, or this is not a book, these are my notes, you would maybe with your finger follow and go from left to right and then go down. We can kind of think of the equivalent of this mechanism, your finger following it, as the thread of execution right here. So JavaScript is a single-threaded and synchronous language. Single-threaded, meaning that it only does one thing at a time, and synchronous, that it does these individual things in a certain order. There are other languages, other programming languages that are multi-threaded. JavaScript, single-threading. So we're going to see how our thread of execution moves through our code line by line, and we'll see it demonstrated that in JavaScript, only one thing is done, one thing is executed at a time. We, as I said, kind of basics of the internet, basics of programming, we have data. This data can be can be certain numbers, it can be strings. Sometimes we have this kind of funky data that's either true or false, but anyways, we need a place to store all of this data so that in our code, we can do things to this data. We can edit it, we can delete it, we can move it somewhere else. And so the place in our JavaScript mental model that we're going to see drawn out in a second when we start diagramming, this is called memory. We have global memory that is available to our entire application. And then we'll see as we get into the diagramming, we also have local memory that is just available to the current function's context that's currently running. As we run through our code, we are going to have, we'll see examples of this tonight. We're going to have multiple functions that are invoked or that are called, that are executed at certain times. And as we said, JavaScript only does one thing at a time. So we also need some place to keep track of which functions are currently running. And so we'll also see where this mechanism called the call stack comes in to help us keep track of what function is currently running. So I've been talking about functions here. Well, functions help us to achieve that goal I talked about of keeping our code dry, of not repeating ourselves. A lot of times when we're coding, we have some functionality that we need to do. We have some functionality to somehow manipulate or change or do something with this data that we're storing in memory. Well, if we're doing the same functionality over and over and over again, we should have some mechanism to be able to store this functionality, package it up, and then use it multiple times. Well, that is what functions do. We can store a certain functionality, a function, what we call a function definition. We can store it at a certain label, and then we can invoke that function, which is indicated by when I invoke a function. How do I know that I'm invoking a function? What is that? What are those things that are included after the function name to say that I'm invoking it? Anyone here know? What do we see when we know we're invoking or calling a function? Yeah, Ian?
The parameters in the parentheses.
Yeah, it's actually when it's the parentheses. Yes. When we pass something in, is it called a parameter or an?
A call.
Starts with A.
Starts with what?
Starts with an A.
I think I might not know.
No worries. It's an argument, but you're totally right.
Oh, argument. Oh, sorry.
We'll go into the difference in a second here. But Anyways, looking here to the code that we have on our right, having just kind of introduced this idea of functions, in this case, the function that we have here, we know it's a function because we have this function keyword. This here multiplied by 2, this is the label for our function. This is how we're going to refer to the function definition that's associated with this label multiplied by 2 in our code. And so the function definition in this case is everything here. It's all of the code that is inside these curly braces. And it also includes the parameters here, which as Ian had mentioned, parameters are the kind of almost placeholders for data that we're going to pass into our function, that we're going to do something with. Looking down to the next line here, so here we saw, this was a function definition with the label being multiplied by 2. If we go down to this line right here, we are declaring a constant variable with the label output, and we are assigning it to the value of this function multiplied by 2, this function invocation, passing in this argument of num. So the difference between arguments and parameters are in the function definition. Arguments are the actual data that is passed into the function invocation. And when I say invocation, when I say we invoke a function, we can also use the terms call a function, or execute a function, or run a function, where basically that functionality that we stored under that function label, where we want it to execute or to be done again. All right, cool. So let's go through this first. All righty. So who would like to help me out with this first diagramming that we have? Dylan, we have a volunteer. Dylan, awesome. So here, for those of you, maybe this is your first time seeing it, this is our mental model of how we diagram out JavaScript code. This is like a very Codesmith special thing, very valuable to understand how our code's working line by line and under the hood. So we start in what we call a global execution context. You can see I already have that written out here. And we are, within, as I said, we need a place to be able to store our data. And Dylan, what is this? What do we call this place where we're going to store data?
Our global memory.
Our global memory. Awesome. Ooh, I lost my black pen. There we go. Global memory. So this is where we're going to store data. Awesome. And then, so we're in the global execution context. As we go to invoke individual functions, we're going to need something that helps us keep track of these local execution contexts. Do you know what is that mechanism that helps us keep track?
It's going to be our call stack.
Yeah, over here. So we kind of denote it with this drawing here. Call stack. And the call stack is where we store the execution context, or the functions that are currently running. And as I said, we always start in a certain execution context. What is the label of this stack frame in our call stack right now, Dylan?
It's going to be our global execution context, or global with parentheses.
Yeah, we can call this. So each of these, we're gonna continue to stack these on top. We can call this our global stack frame.
Global stack frame. Noted. Thank you.
All right, cool. And then Dylan, there's one more piece that I talked about. What is that thing that weaves through our code line by line?
It's going to be our thread of execution.
Yeah, up here we have our thread of execution. And the thread of execution right now, before we jump into the code, and we just open up this, this little program we have down here, this is going to start in global. So let me just go ahead and put some line numbers in here so we can technically communicate using those. All right, awesome. So I think that we are ready to start diagramming this out. So what's happening on line 1, Dylan? What does the interpreter see here?
Yeah, so we're gonna declare a variable labeled num and assign it to the value of 3 in the global memory.
Awesome, beautiful technical communication. So as Dylan said, yes, we are declaring this variable with the label of num and assigning it the value of 3. Beautiful. All right, next line, what's happening?
We're then going to declare a function labeled multiply by 2 and assign it the value of a function.
Yep, multiply by 2. So we declare multiply by 2 in global memory. And you're right, we are assigning it the value of a function definition. This little box with an F with an arrow through it, this is how I'm going to denote, and how we denote at Codesmith, a function definition. And so this function definition, Dylan, if you could let me know what lines is this function definition on?
So it includes, I mean, it's 2, 3, and 4, and I guess technically 5 as well.
Yeah, we have that little curly brace, but just so everyone sees, this is the function definition that I'm talking about. So when the interpreter gets to line 2, it sees that function keyword. It goes, all right, this is a function that I am declaring. And so I'm going to store this whole function definition under this label of multiply by 2 in global memory. Awesome. And then once we've stored that function in global memory, what line do we then move to after that, Dylan?
We're going to move to line 6, and we're going to declare a variable labeled output and assign it the value of undefined to start.
Yeah, so it's not, we don't explicitly give it the value of undefined. It's sort of, it's a little silly, the difference, but it's just not defined right now because, and how do you know that, what needs to happen for us to get an actual value here?
The function multiply by 2 is going to be invoked with the argument num. So it has to go through the function in order for the undefined to become defined.
Exactly. Yes. We are going to, so the result or the value that will eventually be stored at this label output in global memory, we can say it's the evaluated result of invoking the function multiply by 2, passing in the argument num. So awesome. All right, so we are here, we have a function invocation. We know because we have these parentheses here after the function name, and it's not preceded by this function keyword. That would mean it's a function definition. So here we have a function invocation. And Dylan, what do we do? Where are we going to run this function's code? What do we need to open up to do that?
So we're going to open up our local execution context. We're going to have our local memory on the right-hand side.
Yep. So here, this purple box that I'm drawing right here, this is our local execution context. This is where all of the multiply by 2 functions code is going to be run. And as Dylan said, we also have over here our local memory. Yeah, that's fine. This really should, hold on people, just so this is not confusing. There you go. We have our local memory here. Awesome. So we've opened up this local execution context kind of simultaneously as we open up this local execution context. When we hit that function invocation, what else happens? What else? Yeah.
We're going to pop on multiply by 2 onto our call stack.
Yeah, so close. So is it, do we pop on, or what is the other P word we use when we're adding?
That's pop off. We're going to push it onto our call stack.
Yeah, perfect. Yes, we multiply by 2, passing in num. Right, when we're adding something to the call stack, we push. When we're removing something from the call stack, we pop. These are just these specific terms. Awesome. Okay, and then also our thread of execution at this point would weave into this local execution context. All right, great. So now that we have our setup to run this multiply by 2 functions code, what is the first thing that we do when we enter an execution context? What do we have to process?
So we're going to process our parameter input num. We're going to assign that. We're going to, I guess, declare that as a variable in our local memory and assign it the value of num.
Yes, exactly. So
Which
this
is free in global memory.
Yeah, this awesome. This parameter here, as we call it, what comes in these parentheses immediately after the function label in the function definition. This we can think of as like a label for some data that we're storing in this local memory. So input number here is the label, and as Dylan said, the value that is associated with this input number, it is whatever we passed in here where the function was invoked as the argument. So here, this is the argument. Here, this is the parameter. So, so Dylan, you said that input number is going to be assigned the value of num, which is totally correct. And then you said, okay, it's actually going to be the value of 3. Can you walk us through how did you know, like where did the interpreter look to find the value of num? How does it know it's 3?
Yeah, so it's going to reference our global memory where we assigned the value of 3 to them.
Yes, so it's going to, the interpreter is going to look in global memory, it'll look for the label num, it'll see that it does in fact exist, and so we will store 3 as the input number. Awesome. Okay, so now we have processed our parameter, so now we can move into line 3, the function body. And what's happening here, Dylan?
So we're declaring a variable labeled result, and we are assigning it the value of input number times 2, which is trying to recall if there's like a technical term for that, like the expected. Let's go with input number times 2 for now and see if you correct me.
Okay. Awesome. Yeah, input number, it's going to, the interpreter will see this input number, and then it's going to say, okay, what's the value of input number? It will first look in local memory. It's going to find it right there. So we know that input number is really the value of 3. We'll do 3 times 2, which the math majors here probably already figured this out, but that is 6. And so then we move to line 4. And what does line 4 tell us to do, Dylan?
Yeah, real quick before that, it looks like Ian just wrote evaluated sum. Is it appropriate to use that for, I guess, input number times 2? Because that was what I was trying to that was what I was thinking about, but I wasn't sure if I should say it or not.
Yeah, I think here evaluated product would make sense because it's multiplication. But yeah, you could use that. That makes sense to me. The evaluated product.
Yep. Product, yeah, sum would be for a plus sign. Okay. Going to line 4, we're going to return result in our local execution context. The result being 6.
Yep, we have this return result. We know the result is really 6. And so where do we return this 6 out to?
So we're gonna return results into, well, it's already been in our local memory, so we're going to put it into output in our global memory.
Yep, there it is. Output. Now we have output assigned to the value of 6 in our global memory. Awesome. So we've reached the end of this function. So at this point, this local execution context becomes eligible for garbage collection. So JavaScript is very efficient, and as soon as it doesn't need to store any data anymore, it will garbage collect it. It will delete it. It's gone. It's no longer available to us. But this is a mechanism that it used to save space and be more efficient. I'm going to denote that by these red X's here. This has become garbage collected, or you can also say eligible for garbage collection. JavaScript will handle it whenever the heck it wants. So once this execution context has been closed, what else do we need to do to symbolize that in our diagram that it's no longer in kind of control of the interpreter, Dylan?
I don't recall if we pop off the call stack or move the thread of execution out first, but we are going to pop off the call stack, it looks like first, and then the thread of execution is going to move out of the local execution context and back into the
exactly. They happen probably there. It's pretty simultaneous. But yeah, both of those steps happen when we close an execution context. All right. Awesome, Dylan. Let's keep it going, Dylan. So now we just evaluated line 6. That was where we stored output in global memory. So what's going on line 7 here?
So we are going to declare a variable new output and assign it the value of the expected I guess product of multiply by 2 with an argument of 10, which is going to be undefined for now.
Yeah, it's the evaluated result of invoking by 2, passing in number 10. Awesome. So what's going to happen here? We're invoking a function again. So we're going to be opening up another local execution context. When that happens, we'll also be, pushing that new stack frame onto the call stack. Here, we'll run through the function's code, and then whatever is returned from the function, in our first case, it was 6, that's going to be returned out here. I'm not going to walk through that whole process just for the sake of time right now, but that same thing would happen again with the local execution context being opened. All right, awesome. Thank you, Dylan. Thank you for being brave and for doing an excellent job technically communicating through that. If anyone else would like to help me out with the diagramming, you will have the opportunity in just a second here. So be ready to volunteer. All right, awesome. So we just went through kind of this fundamental mental model that we use. Another important point that helps us lead up to our topic of closure is that functions can have multiple names. So as we saw on the last slide, we had a function, which we have the exact same function over here, with the label of multiply by 2. In this case, this is the label, and then the function definition is everything I have in green here. This is the function definition, the actual functionality that we're bundling up and storing under this label. We also remember we use this symbol to denote a function definition. So we have the function label here. We have the function definition, and these two parts together combine what we call a function. So something that's important to note is that these labels, whether it's a function label, or if it's a function label, they're really just pointers to a place in memory where the function definition is stored. And so what this means is that we can have multiple labels pointing to the same function definition. And why would we want to do that? Well, remember, we're always trying to be dry. We're always trying to not repeat ourselves. So if we have one function and we want it to be referred to by 2 labels, it makes sense to just have them point to the same function in memory instead of recreating, like copy and paste that exact function again. We don't, it's a waste of space. So what we're going to see in this code coming up is that we are able to store or have multiple labels point to the same function definition. Alrighty. So here we go. We have our global execution context. Who would like to help me out walking through this diagram? Jennifer, awesome. Thank you for volunteering, Jennifer. Cool. Let's complete kind of the base setup for this diagramming right now. So what do we have over here on the right? Where do we store data?
The global memory.
Yeah, awesome. Global memory. And then what is that mechanism that we use to keep track of the current execution context that's running?
A call stack.
Yep. Here we go. The call stack. And what stack frame always starts at the bottom of the stack?
The global
Global, right. It's associated with this global execution context here. Awesome. And then we also have our thread of execution, which I am just going to abbreviate as our toe. This toe is going to weave in and out of our execution context as we move through our code. Awesome. All right, Jennifer. So let me go ahead and again, let's give ourselves some line numbers. So what's going on line 1, Jennifer?
We're going to declare a function called multiply by 2 and store the function definition
Yep. And where are we declaring this function?
in the global memory.
Global memory, exactly. We can see that here. It's just a little bit more specific communication. Awesome. So we've stored this function with the label multiply by 2, and we've assigned it the value of this function definition. Remember, the label and the definition combine to create a function. Awesome. And then Jennifer, what line does the interpreter go to next?
Line 5.
Line 5, exactly. The interpreter, the thread of execution does not enter a function definition. It doesn't even look at what the definition is until it's invoked. So great, we move to line 5. And what's going on line 5, Jennifer?
We're going to declare a constant in the global memory called output, and it's going to be equal to the evaluated result of invoking multiply by 2, passing in the value 9.
Yep, beautiful technical communication. So because we are invoking a function, what do we need to open up?
A local execution context.
Right. So here we have our local execution context, and within here we've got our local memory, local execution context. And what happens kind of simultaneously as we open up this execution context?
We're going to add the multiply by 2 stack frame to the call stack, and we're going to weave the thread of execution to the local execution context.
Awesome. Yes, we push this multiply by 2 stack frame onto the call stack, and our thread of execution is going to weave on in to this local execution context of multiply by 2. All right. So at this point, we are now in our function definition. This is the point where the interpreter is actually going to look and see what's inside of the function definition. So what is the first thing that we do when we open an execution context? What is the first thing that we process?
We pair the arguments and the parameters.
So what is our parameter label in this case?
Input number.
Yep, input number. And what is the value that's going to be stored here?
9.
9, exactly. It is what we passed into the invocation down here. Awesome. All right. So we've processed our one parameter. We've paired it with its value coming from the argument. And so what is the next thing happening in this function definition?
So we're going to go into line 2, and we're going to declare a constant result. And that's going to be equal to input number times 2. So
yep. And input number in this case, what is the value?
9.
Yep. The interpreter at this point, when it hits this part of line 2, it's going to go, all right, I see this label for some variable or something. I'm going to look in local memory. Okay, we have an input number. Its value is 9. And so we're going to do this multiplication here, 9 times 2, which what do we get for that, Jennifer?
18.
18, awesome. And then what is the last thing that is happening in our function?
We're going to return that result to output.
Yep, we return result, which we know the result here is 18, and we return it out to output in our global memory. So output now has this value of 18 in global memory. Awesome. So we've reached the end of our function. We've run all the code that we had to run. So now what happens to this local execution context?
We garbage collect it. We weave out the thread of execution, and we pop out the multiply by 2 from the call stack.
Yes, we pop off from the call stack. Awesome. Alrighty, so very cool. We just finished completing what line 5 was asking us to do. Jennifer, let's do line 6. What's going on line 6?
We're gonna declare a constant called new label for multiply by 2, and we're assigning it to the label multiply by 2.
New label for multiply by 2. So here, yes, we have multiply by 2, which you're correct, is a function label. But when the interpreter sees this multiply by 2, it's going to do the same thing that it always does. And it's going to go, okay, this is a label for something. I need to find the value of this. And so where is it going to look for the value of multiply by 2?
In the global memory.
Yeah. And does it find it over here in global memory?
It does.
Yeah. And what's the value assigned to multiply by 2 in global memory?
It's the function definition.
Right. It is this function definition. And so what's actually going to be stored under this new label for multiply by 2 is this whole function definition. And remember what I said on the last slide, function definitions, we can have one function definition as we do in this case, everything here. But now it's being pointed at by 2 different labels. So it's now the same function definition is being pointed at by multiply by 2, as well as this new label for multiply by 2. So the same function definition can have multiple labels. That's the important takeaway from line 6. So let's see how that works out when we get to line 7. What's going on line 7, Jennifer?
Now we're declaring a constant fresh output, and that's going to be the evaluated result by invoking new label for multiply by 2, passing in 10. I think that says.
Yes, sorry, it's a little covered by my series of pens, but yes, we are invoking exactly. Fresh output is going to be assigned to the value of the evaluated result of invoking the function new label for multiply by 2, passing in the argument of 10. So we're invoking a function. What do we have to open up in order to run it?
Another local execution context.
Yep, local execution context right here. What happens simultaneously with respect to our call stack?
We're gonna push in the new label for multiply by 2 stack frame onto the call stack, and we're gonna weave the thread of execution into this local execution.
Yeah, let's see. I definitely am not going to be able to fit this all in this narrow call stack I drew, but that's okay. We draw outside the line sometimes. And we pass in 10, right? We push new label, or we push the stack frame associated with new label for multiply by 2 onto our call stack. It's now in control of the interpreter. Our thread of execution is going to weave its way in to this local execution context. Awesome. We're now ready to execute code. What's the first thing we do in an execution context?
We pair the arguments and the parameters.
In this case, what are those? What's the parameter? What's the argument?
So the argument is 10, and the parameter would be, is it input number?
It is input number. So what you'll notice here is that even though we now on the call stack have new label for multiply by 2, whereas before it was just multiply by 2, we're looking at the same function definition. Again, it's this 2 labels pointing to the same function definition. So once again, our parameter label, or rather kind of the label of this data we're passing into our function is input number, and the value here is going to be 10, because that's what we're, see if I can just for a second, no, doesn't like that. There we go. So y'all can see down here, new label for multiply by 2, passing in 10. All right, great. So we have processed our parameters, we've paired them with our arguments. What is the next thing that we're doing in this function?
We're gonna declare a constant result, and that'll be the result of input number times 2.
Yeah, oops, wrong place.
So 10 times 2 is 20.
Yep, exactly. We have our results here in local memory. And we know that we were doing input number multiplied by 2, which I'm not going to draw this out here, but this would be 10 times 2, which equals 20. And then the last thing in this function is return result. Where are we returning this result out to, Jennifer?
Into the global memory under fresh output.
Yes, we have this value of 20, and we are, that's what result is, returning it out to fresh output. And now fresh output is assigned to this value of 20. Awesome. We're done with this function. So what happens at this point to the local execution context?
We garbage collect it, weave out the thread of execution to global execution, and pop off the new label for multiplied by 2 from the call stack.
Yeah, awesome. All right, there we go. It's gone. We are now back in our global execution. We have done everything that this code was asking of us. We are finished. Everyone give a round of applause for Jennifer. Amazing technical communication. Jennifer, are you currently applying to an immersive program?
Yeah.
All right, cool. Have you done a technical interview yet?
No. Kind of
Well,
nervous for that. So, no.
Good luck, but from what I've seen tonight, I think that you are going to be well prepared when you get to that point. So thank you for helping me out there. So we're about to start talking about closure. I would like to take a quick 4-minute break. So we're going to meet back here at 53. Feel free to turn your camera off and mute yourself. But yeah, we'll meet back here in 4 minutes. Go to the bathroom, get a drink of water, and we'll get right back into it. All right. All right, everybody, let's make our way on back. We're going to get started once again. All right, awesome. So functions. So, okay, we went over through that last diagram. We know now that functions, the same function definition can be pointed to by multiple labels. So another thing that we're going to see demonstrated in a diagram coming up right now is that functions can be returned from other functions in JavaScript. So we saw in some of our past examples, you know, we were like returning result, which in this case we knew was a number. Well, as it turns out, functions can return other function definitions. And so we are going to diagram right now through this code snippet here, and we're going to see that proven. So who would like to help me out and diagram through this? Do I have any volunteers? Augustine, awesome. All right, let's do it. So Augustine, if you could just help me get these kind of components I have here labeled. What do we have over here on the right where we store data?
It's going to be our global memory.
Awesome, global memory. And then over there on the left, the thing that helps keep track of what execution context is running, what's that called?
That is our call stack with our global stack frame.
Amazing. Did not even have to ask you. Global, there it is. We always start with it at the bottom. And then we also have our beloved toe over here running through our code line by line. Awesome. Will I get these line numbers written? Could you let me know what is going on line 1 in our code, Augustine? What do we got to do?
Sure. So on line 1, we are declaring a function with the name create function in our global memory. And we are, for now, assigning it the value of the function definition.
Awesome. Yes, we store it, or we declare this function with the label create function in global memory and assign it the value of this function definition. Beautiful. And then Augustine, what line does the interpreter go to next?
And then we would go down to line 7, where we are declaring a new constant generated func and assigning it the evaluated result of invoking create function.
Yes, exactly. The evaluated results. Augustine, your voice is so similar to one of the residents in my program right now. It's kind of crazy. But I'm looking down at the iPad and listening to you talk. I'm like, that sounds good. Yeah, wow. Okay. Very cool. So yes, we are going to invoke this function, create function. And so where is this function running going to happen? What do we open up, Augustine?
We're going to open up a new local execution context.
Yep. And in this local execution context, we have our, it's not very straight, but you get the point. We have our local memory. What happens simultaneously as we open up this local execution context?
We are going to push the generated func equals create function stack frame onto the call stack.
Yeah, so correct. That is the whole line that we're processing right now. But when we label the stack frame, we're just going to label it with the function that's being invoked. So which is the function here being invoked?
Gotcha. That's going to be create function.
Perfect. Right there. Create function. Awesome. All right. And then our toe is going to weave into this local execution context. Beautiful. So all right, so now we are in our function definition, which we have over here. And does this function have any parameters?
Yes, it does. I see num as the parameter.
So let's remember here we are, this execution context is the execution context of create function. That's the
Right.
that's the function that we're invoking here. So does create function have any parameters?
No, it doesn't.
No, it doesn't. How do you know that? What are you looking at to know that?
I'm looking in between the parentheses to see if there's a parameter, which I do not see.
Exactly, right here. If there was a parameter, then it would be in these parentheses, but Augustine's totally right. There's no parameter because there's nothing inside these parentheses, which is common. Functions don't have parameters sometimes. If it did have a parameter, the first thing we would be doing in local memory here would be pairing the parameter with its value coming in from the argument. As you can see here, also don't have an argument. And that makes sense because if a function has no parameters, passing it an argument, it's just going to ignore it. It's not going to do anything. So, all right, very cool. No parameters. So now we are on line 2. And what is going on line 2 here, Augustine?
On line 2, we are declaring a new function with the name multiply by 2 in our local memory.
Yeah, in our local memory now. So over here in our local memory of this execution context, we are declaring this function multiply by 2. And what is the value stored here, or the value assigned to multiply by 2 going to be?
Right now, it's just going to be the function definition.
Exactly. It's going to be the function definition. And this function definition that I'm denoting with this F in a box with an arrow, what lines in our code snippet does this function live on?
I don't know if I understood that correctly, but would that be line 2 through 5?
It's actually line 2 through 4. So it is this right here. It ends with that curly brace on line 4. That is the function definition that's being stored under the label multiply by 2 in local memory. So it doesn't include line 5.
Gotcha.
Line 5 is part of the function body of create function.
Gotcha.
Yeah. So, okay, cool. Now knowing that, so we've declared this function, we've stored its, we've stored its function definition at the label multiply by 2 in local memory. Now, what line is next in our execution of create function?
Line 5.
Exactly. And what is line 5 asking us to do?
We are just returning the function definition of multiply by 2 into our global memory under generated func.
Beautiful, beautiful technical communication. I'm going to take one step back. If I'm the interpreter and I see this line 5, return multiply by 2, where am I going to look to find out what the value of multiply by 2 is?
You would look first in the local memory.
And there it is. So that's how that is how Augustine knew that this multiply by 2 is actually just a label pointing to this function definition. So this function definition gets returned out to our global memory and it's now stored under generated func. Remember, this function definition I'm talking about here that just got returned out to global memory is, again, this function on lines 2 through 4. That is what is now stored, or that's what's being pointed at by the label generated func in global memory. So we have just returned a function definition out of a function. Pretty cool stuff. Very crucial for closure. Just coming up in a second. All right, so we are now done executing this create function. What happens to our local execution context, Augustine?
It is garbage collected.
Beautiful.
And then we'll also pop off the create function stack frame off the call stack and weave our thread of execution back into our global execution context.
Yep. Awesome. All right. Very cool. So we just completed line 7. Let's go down to line 8, Augustine. What are we doing here?
Okay, so line 8, we are declaring a new constant with the name result, and we are assigning it the evaluated result of invoking generated func, passing through 3 as an argument.
Yes, exactly. So we have result over here in global memory, and we're going to need to go grab what that evaluated result is. As Augustine said, we're going to be invoking generated func. So we are going to need to open up a new local execution context. Actually, I'm going to use blue color. Awesome. Open up this new local execution context over here. What happens? What gets popped on to our call stack? Or sorry, what gets pushed onto our call stack?
We're going to push the generated func stack frame onto the call stack.
Generated func, this argument of 3. Cool. Toe is going to weave into this new local execution context, which we have just opened up. All right. And so are there any parameters for this generated func function?
Generated func, yes. And our parameter would be num.
Exactly. The parameter label is going to be num. We have it right here. Remember, this is the function definition that we're currently running. So right there, you can see num is our parameter. And what is the argument that was passed into generated func?
Our argument would be 3.
3. Beautiful. Okay. So now we have processed our parameters. We've paired our parameters with our arguments in local memory. Also, by the way, I don't know if I mentioned this, but another word for memory is a variable environment. So I could say that this is a local variable environment, just another term that we can use. Okay, awesome. So now that we've paired our parameters, what is the next line that the interpreter is looking at?
So the next line would be 3 here, which is returning the evaluated product of num times 2 or 3 times 2 since we defined num already.
Return num times 2, right? We already have num is defined, or it is in our local memory or in our local variable environment with this value of 3. So the interpreter is going to go grab that value of 3, and then it will spit out this. I like the term evaluated product. Thank you, whoever got us there. So yes, that is 6. So what is going to be, or rather, where does this 6 get returned out to?
That 6 would be returned back to our global memory under result.
Awesome. There it is. All right. And have we reached the end of generated func? Have we done everything that this function was asking us to do?
Yes.
Yep. So what happens now?
We're going to garbage collect our local execution context, pop off the generated func stack frame, and weave our thread of execution back into the global.
Awesome. I tore down one of the walls of our call stack in the process, but yes, totally correct. We are going to pop off that stack frame from the call stack. So now global is back on top. Our thread of execution is now also back in global, and this local execution context was garbage collected. It's all gone. All of this data that was here is now completely gone, not available to us. Also not taking up space in memory. That's a good thing, but that's important. When an execution context closes, we no longer can access its local memory. We'll see. Maybe we can. Maybe it persists. All right. Thank you, Augustine. That was an awesome job. Thank you so much. Great job. Great technical communication. I also think that you are going to do well in your technical interview coming up. All right.
So, can I ask a quick question?
Yeah.
If that's all right, if you if you put on line 7.5 if you use the variable num for something, like console.log num or whatever, has that variable been declared in the global, like, is it accessible from the global execution context?
Good question. So it would be available to us if it was declared in global memory. So in this case, do we see num in global memory?
No.
Yeah.
But okay, gotcha. But because the function definition got returned, or because the function definition got returned, that argument doesn't exist still. Like, any arguments that are out there are not accessible in the global execution context.
Exactly. In the global execution context, they are not available. When we invoke create function, which is, or sorry, when we invoke generated func, which we know is assigned the value of what is returned from create function. So when we're inside this local execution context of generated func, then we have access to num, but not outside of it. Yeah.
Okay.
Yeah. We're going to see in a second, though, how maybe there is a mechanism in JavaScript that would allow us to kind of be able to access in some way those variables from that local context outside of the original context. Yeah. Thanks for the question. Oh, go ahead.
Yeah, I have a quick question. So on line 5, when we return multiply by 2, that function, how come we are, like, why are there not parentheses after that? Like, yeah, I guess that's my question.
So when we have parentheses after a function label or the name of a function, what does that mean? What does that mean that we're doing? What are we saying that we want to happen to that function?
We're invoking that function.
Yeah, so if we had parentheses on line 5 after multiply by 2, then JavaScript would immediately invoke multiply by 2, and it would return the evaluated result of multiply by 2. So in this case, what we're doing on line 5 is we just want to return the value that is stored at the label multiply by 2. We want to return this, in this case, this function definition.
Oh,
so that's
okay.
why we don't use there.
Okay, that makes sense. Thank you.
All right, for sure. Thank you for the questions, y'all. I was just about to ask for thumbs. So thumbs to show understanding. How are we feeling so far up to this point? Anna's got a thumb up. We've got Meg, Sean, Augustine. I've seen some other faceless attendees, but they have their thumb up. All right, that's good. Any more questions at this point? All right, gonna move on then. Okay, so we have one more diagram. So we have seen that when this, I think, relates. Oh, Sherry, do you have a question? All right, if you have a question, raise your hand again, Sherry. Okay. So something that we are going to see as we diagram out this next snippet is that calling a function in the same function or function call as it was defined in determines what variables we have access to. So where you define your function, like where in your code it is actually declared, determines what variables your function will have access to when you call the function. And so this is going to be important. We're going to do this diagram, and then we are going to see that the variables that are available to us when we invoke our inner function, in this case, increment counter, we're going to see that we have access to these variables inside of the function where increment counter was defined. And so we'll see what happens to those variables and whether we kind of maintain access to them as we move through this code. So here we go. Who would like to help me out with the diagramming for this one? Any volunteers? Yeah, Robbie, let's do it.
Yeah, I can certainly try, but I'm confused, but I want to give it my all. So we're going to declare. Go
ahead.
Okay, so we're in the global execution context. We'll have our global memory and our call stack. And we'll be in the global stack level. I don't know what you call that. Thread of execution will be in that global memory, and we're going to declare a function outer.
So the thread of execution, just to be specific, is in the global execution context.
Global execution context
is where we store data or where we store our variables within the global execution context. Just to be exact there. But yeah, let's go ahead. What's going on here on line 1, Robbie?
On line 1, we declare a function outer with no arguments. And we're going to store that in the global memory.
Yes, we have this function with the label outer. I don't know where that second line came from. And we are assigning it the value of this function definition. You're correct that outer does not have any parameters here. However, if we are the interpreter at this point, when we're just saving the function definition at this label of outer, the interpreter doesn't even look into the function definition. It just goes, oh, we're declaring a function. It has this label outer. I'm just going to take everything after it. I'm not even going to peek, and I'm just going to store it in global memory. And it's just chilling there, ready until we invoke it. At that point, we'll look at the function body. But good job.
That
all right.
Answers my question from last. That answers the question I had one ago. That makes perfect sense.
Awesome.
And then we go to line 8, and we're going to call function outer, which adds it both to our call stack and opens a local execution context with for the outer function with local memory and local context.
Yep, we have our local execution context. I'm abbreviating that, as you see here, with its local memory. Awesome. This is for the function outer. We've just pushed the associated stack frame onto the call stack for. Beautiful. And then our thread of execution weaves into this local execution context. All right, great job, Robbie. So now we're inside, we've opened up this local execution context. We're now within the function body of outer. As Robbie pointed out earlier, outer does not have any parameters, so we're not going to be pairing parameters with arguments, but we would normally do that step first. So we just move right into the function body on line 2. And what are we doing on line 2, Robbie?
We're going to declare a variable counter in local memory, and we're going to set that equal to 0.
Awesome. Yes, we're declaring this variable with the label counter in local memory and assigning it the value of 0. Awesome. All right. What about what's going on the next line?
We're going to declare a function in local memory increment counter. And that'll be equal to that blank function for now, or like I don't know. Not undefined, but a function.
A function, yeah, a function definition. We are assigning.
Yes.
Yeah, we are assigning increment counter to the value of this function definition, and the function definition I'm talking about is everything that I have in this, my red blob here. Very cool. So that whole function definition is now stored under the label increment counter in this local execution context's memory. All right, cool. So we've done that. What line do we go to next, Robbie?
I think you would say our thread of execution moves to line 6, where we call increment counter in local memory.
Yeah, that is totally valid. Yes, our thread of execution moves down to line 6, where we are calling increment counter. We are invoking this function. So the interpreter is going to hit line 6. It's going to see this label increment counter, and it's going to go, okay, what is the value of increment counter? Well, you know, we have this parentheses here, so we know it's a function, but the interpreter is going to look in local memory, look for this label increment counter. It's going to see, okay, it's this function definition that I have stored here, which again, in our code snippet is here. So when we invoke a function, let me write out here. When we invoke a function, in this case, increment counter, what do we need to do? Where do we run this function body?
Yeah, we need to set up a new execution context, extra local execution context for increment counter, and we're going to add that to our call stack as well.
Yep. We have this, the inception, the local execution context within another local execution context. I like the super local execution context. There we go. Also is going to have local memory. So for anyone, if this is the first time you're seeing it, yes, we can have execution contexts inside of execution contexts. And when that happens, you'll notice there will always be multiple execution contexts on the stack. That's kind of if those correlate to each other. All right, awesome. So we are now inside of increment counter. And what is the function? Or first of all, does increment counter have any parameters?
No.
No, it doesn't. There's nothing in these parentheses after the label right there. Correct. So what is happening in the function body of increment counter?
It's going to look at counter, which exists in the super local memory, and it's going to add 1 to it.
Yes. So, okay, that is totally correct. Let's just take I'm just going to take one step back. So counter, first of all, counter plus plus, this is our increment operator, as it is called. So this means we're adding 1 to whatever the value of counter is. So Robbie, where is the first place when the interpreter hits this counter? Where's the first place where it's going to look?
It'll look at that green local memory.
Yeah, it's going to look right here, the current execution context local memory. And there's nothing there. Counter is not there. So where does it look next? Where does the interpreter go next to find this value?
It'll go up a level to the increment counter's local memory. And it'll see counter equal to 0.
Yeah. It's this actually, the pink one is outers.
Outer. Oh, I'm sorry. Oh,
yeah,
right.
Exactly.
It's written in pink. Yeah. Sorry, that makes sense.
No worries. Totally correct though. Yes, this is the place within this pink execution context, outers execution context. Memory is the next place it's going to look for the value. Now, Robbie, if let's say that counter wasn't here, where would be the next place that the interpreter would look?
In global memory.
Yeah, exactly. It would look here. So the interpreter, when it's looking for the value of some label that it's come across, it's going to look in the local the current execution context, and then all of the execution context outside of it. So great. But yeah, in this case, it does find that counter has this value of 0. And so it is going to, as you said, it is going to increment the value of counter here to 1. So now counter within outers, the execution context for this outer function within its local memory, it's now assigned to the value of 1. So we've incremented it. Awesome. Cool. Is there any more code left to run within our increment counter function?
Is there any more code within no?
So totally correct. Here, we just did this line 4. We hit this curly brace. It tells us you're done with the function. So what's going to happen to this inner green execution context?
It'll get garbage collected, and the increment counter call level will pop off the call stack.
Yeah, the increment counter stack frame will be popped off the call stack.
Stack frame.
Stack frame, yeah. Cool. So now we are back in the pink local execution context. These X's signify that this green execution context is not here, but I don't want to erase it because maybe some people are still going to reference it. So now we're out in this, we're back in the pink execution context. And is there any more code left to run within outer?
No, there isn't.
No, correct. What we just did, the whole reason we opened that green inner execution context was because we were invoking this increment counter on line 6. We hit line 7, function is done. So this local execution context for outer is also going to be garbage collected, and it is also going to be, the associated stack frame will be popped off of the call stack. So we are now back out in our global execution context. I always tear down the walls. There we go. And we have just global left on the call stack. We're done executing this code. Great job, Robbie. Thank you. Thank you for helping me out. Awesome job. I'm glad to hear that kind of helping me with the diagram answered one of your questions. That's totally the goal of this. I think everyone else can take a lesson. It's good to volunteer, good to do this in front of other people. All right. So we have reached the end of this code. And what we'll notice here is that because we invoked this increment counter function within the same context where it was defined, aka within this outer function's function body, we've now lost access to any of the variables that were also defined at the same level, the same context. So what I'm talking about here is counter. So when we invoke this outer function, we know that part of the functionality of outer was invoking increment counter. And increment counter, had this counter variable, or rather, it accessed the counter variable in outer's local execution context here. So let's say that we didn't want to lose access to counter. We didn't want it to just get garbage collected and be gone forever. Well, there's a certain organization of our code, or rather a certain place where we can call functions, declare functions, and then call them after, that allows us to keep some of this data from within the local execution context and make it accessible outside of that current execution context. So we are going to see that in a second here. So again, big point to focus on: where you define your function determines what variables your function has access to when you call the function. So what we're going to see, looking at this code here, it's similar to the last code we looked at. We have our function outer, appropriately named because it's the outer function in this case. Inside of outer, we are declaring this variable counter, and then we are also declaring this function increment counter. But in this case, we are returning increment counter, or rather the function definition stored at increment counter here. And so we're going to see, when we assign the evaluated result of outer, aka the return value of outer, which is this, what I'm pointing at right here, this increment counter, when we store that returned value of outer into a new constant or under a new label in global memory, and then we invoke it, we're going to see some interesting stuff. We're going to be introduced to these kind of new concepts. Again, how can we persist data, things like counter, between function calls? And how does where we define our function determine what data we have access to in those subsequent function calls? Alrighty, who is helping me out with this one? We've had some great volunteers so far. We're at this point in the lecture where I'm just going to get this set up for us, and I'm going to look up whoever has their hand raised. Sebastian, you are going to help me out with this one. I did see that there were other hands, so I remember who those people were, and so one of you can help me out with the next code that we're going to walk through. But Sebastian, you were first. So So let's do it. All right, again, as I'm drawing my line numbers, I always forget to do this in my setup. What is going on line 1 of this code snippet that we have down here in the corner?
All right, we're declaring a function named outer and assigning it the function definition.
Yep. And more specifically, that's totally correct what you said. More specifically, where are we declaring this function outer?
In our global memory.
Yep, exactly. Exactly. Cool. So we have declared this function with the label outer in global memory and assigned it the value of this function definition. What line do we move to next, Sebastian?
We're gonna go ahead and move down to line 8, I believe.
Yep, exactly correct. And what's going on in line 8?
We're going to declare a const named my new function and assign it the evaluated result of calling the function outer.
Yep, exactly. We're going to call outer. We see these parentheses here. That means it's being invoked. So we are going to open up a new what, Sebastian, to run this code?
Local execution context.
Yep.
And new local memory. And we're gonna, sorry.
No, go ahead, keep going.
We're gonna push my new function. Is it my new function or outer?
So which function are we invoking here?
Outer.
Outer, exactly. Yeah, it's the function, whichever function that has the parentheses directly after it, that's the function we're invoking, and that is the name of the label of the stack frame that we're going to be pushing to the call stack.
All right
there. I totally forgot to include the toe in the setup, but it is there, and it's now
weaved into.
Yeah.
And now we're going to go ahead and move into our function definition body. And we're going to declare a counter variable and assign it the value of 0 in our local memory.
Yep, exactly. We're going to declare this variable with the label counter, assign it the value of 0 in our local memory. Awesome, great job. Keep going, Sebastian. What's happening on the next line?
We're going to go ahead and declare a function increment counter and assign it the value of a function definition.
Yep, exactly. We're declaring this function with the label increment counter and assigning it the value of this function definition. Everything here from lines 3 to 5. All right, and then what line does the interpreter go to next?
Line 6, and it returns increment counter. So just the function definition of increment counter back to the I get confused here. Is it the local memory or is it the global memory?
So we are currently in the local execution context of outer, and we're returning something. So when we return a value out of a function, where does that value go?
To the last execution context. So would that be the global execution context and the global memory?
In this case, yes, it is we're returning it out to global memory. Specifically, it's going to be stored, the function definition or the return value of outer is going to be stored under the label my new function. And we know that because this return value is going to be returned to wherever the function was invoked. So outer was invoked right here as kind of what's going to be the value of my new function, and my new function is a constant that we're declaring in global memory. So it's out here in global memory. Awesome. All right, cool. So are we done executing outer's function body, Sebastian?
Yeah, we returned increment counter. Yep, we're done. It's eligible for garbage collection, and we can pop off outer from the call stack and weave our toe back into our global execution.
Awesome. Yes, we have now cleaned up from that we've done our, yeah, it's this local execution context, as you said, is eligible for garbage collection. Pop that stack frame off of the call stack. Awesome. So what line are we on now? What line is the interpreter going to handle next?
9.
9, exactly. And what is 9? What is line 9 asking us to do?
It's invoking my new function.
Yep.
Yep.
And so what do we, when we invoke a function, what do we have to open up?
New local execution context and a new local memory.
Yep, new local execution context, which has its own store of data or its own variable of environment or local memory, as you said. And then what happens to the call stack?
On the call stack, we're gonna go ahead and push my new function, my new function stack frame onto the call stack.
Yeah, nice, very nice. Cool. All right.
And then we're gonna weave the toe back into the local execution.
Awesome. All right. Does my new function, so first of all, Sebastian, when we're in this, we've just opened up this new local execution context for my new function. We have my new function stack frame on the call stack. What lines in our code snippet does the function definition of my new function live on? What lines are we looking at?
The global memory. Oh, sorry. 9 and 8, 9, 10.
So 8 is where we declare my new function, and then 9 and 10 are both invocations, but where is the actual function body? Like what, my new function is a label that's pointing to a function definition. What lines in our code snippet actually make up this function definition?
3, 4, and 5. So it'd be increment counter.
Yeah, exactly. It's 3, 4, and 5, because remember, if we take these kind of steps backwards, we invoked outer, and then we stored the return value of the outer function in this my new function label. So the return value of outer, if we now go back up to the outer function, the return value is increment counter, which is this function that we've declared just above it. So when we are in this new local execution context, this is what we're looking at. So my new function, does it have any parameters?
No.
No.
Oh,
It has no.
yeah, no.
Yeah. So we jump right into the function body. And what is this function body asking us to do?
It's asking us to increment counter by 1.
Yep. This counter plus plus is asking us to increment counter. So Sebastian, normally, or no, always, when the interpreter sees a label like counter, where does it look? Where does it look for the value?
And this, whichever scope memory it's in, which so
yeah, exactly. So it's first going to look in the local memory of the execution context we're currently in. I don't see any counter. There's no counter there. And when it looks out to global, we also don't see a counter here. So what the heck do we do? What is going on here? Does this just not work? Do we hit line 4 and it just errors and goes, I can't find counter. Where the heck is it? It's not in local memory. It's not in global memory.
So is that what they call a scope link? Or not? I think it's called a scope link, but it's a scope and then the 2 brackets around it.
Yes, Sebastian, you are leading me to, this is a pinnacle moment of the lecture right here. We are getting into closure. So yes, I'll get to the bracket scope in a second. But so what's happening here? So when we returned increment counter, this function definition, out of the local execution context of outer, we returned this function definition, and I didn't quite diagram out everything that happened on the step. Something else came along with this function definition. And what came along with this function definition that is now stored out here as kind of a little piggybacked onto our my new function definition is all of the variables that were declared in the same context where increment counter was defined. So I'll say that again. When the function definition of increment counter was returned out to global memory and stored under this label my new function, a couple things came along with it. A couple things kind of got backpacked along or piggybacked along with the function definition. And those things are all of the variables that were declared in the same context where increment counter was declared. So out here now, with kind of linked on to this my new function, we have counter with its value of 0. So this is a very, very crucial part of understanding JavaScript and understanding closure. This here, this sort of packaged up this package of all of the variables that were from that same context, from that same local memory where increment counter was first declared. We refer to this at Codesmith as the backpack because, you know, as I said, it's kind of like this increment counter function. It was born within, it was originally declared within this local context, and then it went on a journey out to global memory, but it brought a few things along with it. It brought this counter variable because they were born in the same place, and it's coming along with it. So from now on, whenever my new function is declared within this, any of these local execution contexts of my new function, any of the following invocations, we are going to have access to the variables stored in this backpack here. So that's why when we hit line 4, this counter plus plus, even though counter is not in this local memory, JavaScript is going to go, okay, I need to also look in the backpack. Another word where there's a slide coming up covering this in a second, but another word for backpack, we like using the term backpack at Codesmith, is a closure. This is a closure. And as Sebastian was saying, this isn't totally crucial to your understanding of how closure works, but it is actually, if you go and you test this out in the code, this backpack does get stored under a property with this label bracket, bracket, scope, bracket, bracket. Again, not super important, but you were totally correct there. That is technically where these closures get stored. If there were more variables that had been declared here, or rather, I guess, here in the code, those also would come along and be stored in this backpack, and we could access them from within the local execution context of my new function. All right, cool. So now that we've introduced the backpack, Sebastian, we're now back on line 4. We see counter plus plus. And so what is going to happen to the value of counter out here in our closure?
It's going to be incremented to 1.
Yep, exactly. It's going to be incremented to 1. It is now changed. All right. Is there any more code left to run in my new function?
No.
Nope. No more code. So
We are eligible. Sorry.
Go ahead. You walk me through how JavaScript's going to clean this up.
So it's my new function's local execution context is going to be eligible for garbage collection, and the thread of execution is going to weave out back into the global execution context, and the my new function stack frame is going to be popped off the call stack. Amazing.
Yep. That's how we clean up. All right, now what line are we on, Sebastian? I see your hand, Wilton. I'll get to you after we finish this last line 10. So
Line
what's
10.
going on the
We're gonna once again invoke my new function. And we're gonna open a new local execution, a new local memory. We're gonna also put the stack frame menu function onto the global call stack and then weave our tool back into our local execution.
Value function, beautiful. Yes, and our thread of execution also goes into or weaves into this new local execution context. The wrong color. Great. All right, so now we are in this, whoops, what was that? We are now in this local execution context of my new function. We're here, and so once again, what is the function body of my new function?
Increment counter.
So that's we're looking at the function that within outer was given the label increment counter. And what's in the function body?
Oh, sorry. The counter increment counter by 1.
Yeah. I guess that it's confusing to verbalize this because what we're doing with counter plus plus, you're right, is incrementing counter by 1. And so Sebastian, remind me, where is the interpreter going to find this counter value?
In our backpack.
Over here. Because remember, this is another local execution context also of my new function. And so this, all subsequent calls to this my new function, this one on line 9, this one on line 10, if there was another my new function parentheses on line 11, they all have access to the same variables, to the same backpack. So in this case, this counter value is now going to be incremented again to 2. And that data is going to persist. What I mean by persist is, counter when it was first put in the backpack, initially when we returned out the increment counter function definition and stored it under my new function, that data counter had a value of 0. That value of 0, that combination of the counter label and the value of 0 persisted to this first invocation of my new function. We incremented counter by 1, that data counter with a value of 1 persisted to the next invocation of my new function as well. And then we were able to increment it by 2. All right, awesome. So that is the end of our my new function. So I'm just gonna do this. We garbage collect, we pop my new function off of the call stack. Toe is back out in global, and we are done executing this code. Thank you, Sebastian. That was awesome. Thank you so much for helping out. Great. All right. I see we have several questions. So the first one I saw was Wilton.
Yeah. So I just had a question about closures. So in my new func, when it's looking for counter, does it first look in local memory before it looks in the closure, or does it look in the closure first, or how does that work?
Good questions. Yeah, what's the order? It's going to look in local memory first. So here, when we were in our first invocation of my new function, this was the invocation that came from line 9. If there had been a counter variable in local memory, it was equal to, something, whatever, this would take precedence over what's in the backpack.
Okay. And for example, let's say it wasn't in the backpack as well, then it looks in global, right?
If it wasn't in the backpack, it will look in, yes, it will look in global. So if counter was, yeah, I'll leave it at that.
Okay, thank you.
Yeah. I also, all of these questions of like, what, if you have a counter in the local memory, or you have a counter in the backpack, and you have a counter in global memory, I encourage you to go just write up a few lines of code and test it out for yourself and see how it behaves, because that's really the best way to understand how, how JavaScript behaves. And something cool about code is that we can, test out any of these ideas. So anyways, I encourage you to do that. Thank you for the question, Wilton. Alexandra, do you have a question?
Hi, yes. I might have missed this, but to me, this doesn't seem super dry, right? Because if it's a function within a function, doesn't that seem redundant? Is this a wholly different topic, or wouldn't it just make sense to have one function that you're calling and to bring along that variable counter each time?
Yeah, very good question. So it does not break the dry principle because these are different functions. Like outer is one function with a certain function body, and then increment counter is an entirely different function with different functionality, in a different function body. So when we say that something breaks the dry principle, it's when let's say we had like two identical function definitions that we declared, but they were stored at different labels, that would be redundant because we could just have the single function definition and just have two labels pointing to the one. The reason why part of the reason why you may want to utilize closure, or essentially utilize in order to have closure, you absolutely need an outer function returning an inner function. And then when that inner function is returned, all of those variables that were in that same context where the inner function was declared get brought along with it in the backpack. Part of the reason why you might do that, and this kind of ties into a lot of the practical applications of closure in modern JavaScript development, is that this counter variable now is only accessible from within the function invocations of my new function. It's not available in global memory. Like I couldn't go on line 11 down here, and if I did console log, I hope that's not getting cut off, console log counter out here in our global context, you're going to get an error. It's counter's not defined. I'm drawing it under global memory, but it's not available in the global context. It's only available within function invocations of my new function. So I'll get to this in a second, but this gives us a lot of power when it comes to like privacy. Like if you want certain data to only be available when that certain function is called, you can use closure. Or let's say like, I know I'm kind of rambling now, and maybe you'll have a follow-up question, but this is an example I really like to use. Let's say that you have a video game, and in this video game, characters can open certain doors. And there's like prizes behind those doors, but only the first character to get to the door to like invoke that open door and take prize function can actually get the prize. Well, if you have many characters that are invoking that open door and take prize function, somewhere in that function, you could store like prize has already been taken as true or false. And so when it would change to prize has already been taken true, like the first character has taken it, any subsequent invocations to open door and take prize, that data of prize has already been taken equals true, that's going to persist between those function calls. So all of the characters who come after it are not going to be able to grab that prize. So things like this. Does that help answer your question? Do you have a follow-up question? I know I got kind of
No, it's very helpful. I think the part that I'm still a little hung up on is why not just have function outer, right? Maybe I just didn't understand, but function outer, let counter, and then rather than having a sub function, just have the counter plus plus and then return that. You see what I'm saying?
Okay, so you're thinking like what instead of declaring this function here, we would just do like return counter?
Or yes, and maybe it's just because I'm so new at all of this that I don't understand, but or return counter plus plus, I guess, is what I'm thinking.
Yeah, no, totally the train of thought totally makes sense, especially if you're newer to this. This is complicated. If we were to do this, and then we invoked, let's say that this was our function body, we declare this counter variable using let, we assign it the value of 0, and then we return counter incremented. We would be, let's say that none of this was here. We invoked outer afterwards. This every single time will have a value of 1. Like the data is not going to persist. It's not going to be counter in this first invocation is 1, and then the second invocation here becomes 2, that data is going to be when this outer execution context is closed, all of those variables are going to be gone forever. They're going to be garbage collected. So it's useful to us to use this kind of structure, kind of returning a function outside of another function, if we want that counter variable to persist in those subsequent function calls.
Got it. Thank you so much. I appreciate that explanation. Thank you.
Yeah, you're welcome. Thanks for the question. I'm sure that other people have the same question. So thank you for asking it. Yeah, let's go, Augustine.
Yeah, not sure if this is super important. I was just curious, but I've heard backpack be referred to as closure backpack, like Cove, PLSRD. What is the technically correct way to communicate that?
All of those words that you just used are totally valid and correct. The only one that I would say is less kind of globally recognized is backpack. Backpack is something that I believe Will Sentence came up with that term on his own, and it makes a lot of sense. So we use it, we continue to use it in the hard parts. But the engineers that I was working with at Tatari, I remember I asked them about it once, and they'd never heard of it referred to as a backpack. But we will get there in like 3 slides. We have a list of the different names that this thing can be called. All of those that you just said are valid.
Okay.
But yeah.
Thank you.
Yeah. All right. I see that we're getting to the end of our time, so I'm gonna move on here. But yes, this bond that was created when we returned increment counter out of outer, this bond that was created between this new function label, my new function, and the variables that were declared at the same context as our returned out function increment counter. This bond is created. And we can also say that everything from, the local memory or the variable environment is what ends up in that closure or in that backpack. So the backpack, we've gone over this. I've just explained all of the text that we have on here. You are going to get all these slides sent out to you. I believe tomorrow morning. If it's not later, yeah, I think it's tomorrow. So you can reference these, but we just went over how this all works. So exactly to your question, Augustine, what can we call this backpack? Because backpack is more of just like a Codesmith term. We can call it a closed over variable environment, or COVE. We can call it, if we want to be super fancy and verbose, a persistent lexical scope reference data. I've also heard persistent lexically scoped reference data, but yes, this PLSRD, the backpack, or a closure. So the backpack is attached to this my new function label here through, as Sebastian mentioned, a property known as bracket scope. So if you actually go, if you go write this out and you run this code, like a code snippet like this in your browser, you should be able to, if you go to the dev tools, if you don't know what I'm talking about at all, that's totally fine. If you go to the dev tools, you should be able to see a little arrow down and be able to find this bracket scope property, and you'll see what variables are in there. So anyways, these are the different ways that we can refer to this backpack. Okay, so quickly before we go, just to prove a point, this is the same code snippet that we just walked through. We got from, I'm gonna move this over here. We have already done all of this. So if someone, we're just gonna, you can see the only difference here between the code on the last that we just diagrammed out and the one here is that I've added in this console log counter. So we remember, we stored the evaluated result of outer, which is really this function definition of increment counter, into my new function. When we invoked it the first time, we got the value of 1. When we invoked it, when we invoked my new function the second time, remember that data, that counter with the value of 1 persisted to this next function call. So counter was then have the value of 2. Again, I'm drawing this here because we have this console log. So if we down here do now the same thing, but we invoke outer again and assign we invoke outer again, and we assign to this new label another function, the evaluated result or the return value of outer, which is the same thing that we did here. Now, when we go to invoke another function, again, this label we have here, what do we think is going to be console logged for counter? Anyone have an idea and would want to kind of explain their thinking here? Dylan?
Seems like it would be 1 for the first another function and 2 for the second another function. And I suspect it's because the declaration of another function kind of goes through the process again and creates a new backpack. Yeah.
Yes, exactly. Great explanation. So I remember when I first looked at this, when I was learning about closure, I would have thought that this would be 3 and 4. Like I would have thought, okay, outer is the same function, even though we're storing it in a different label. So it's got to be that same backpack that we're referring to. But Dylan's totally correct. When we invoke outer again in a whole new invocation and we store it in a new label, a new backpack gets created where counter is going to have this initial value of 0. So if we were to invoke my new function again here, then Dylan, what would I expect to be logged to the console here if I had that?
3.
3 in this case. Yeah, exactly. So it would be 3. But the point here is that when we invoke our outer function again and store it in a new label, a whole new fresh backpack gets created that has nothing to do with the backpack that was created and attached to my new function. So that's the important.
Sorry to interrupt. Is that true if my new function was, say, below the second another function? It's like reading down?
Yep. Yeah. So this, let's say we had a 4th invocation of my new function that was down here. What do you think that the value would be here, Dylan?
I mean, it seems like it would be 4, but I could see how it could. I think it would be 4, just because it's not even related to another function. So it would probably just go up and like revisit that initial backpack.
Exactly. Yeah, exactly. It's even though in between the 3rd and 4th function call of my new function that this whole other thing happened, it's not related at all. My new function has actually no knowledge that another function was even created. So yeah, it would be 4. Continue on.
Cool.
All right. Any thumbs on this? Thumbs on the individual backpacks? Any question? Any clarifying questions at this point? Bean2, I hope I pronounced your name wrong, but I like your, not even the thumb, just kind of like the head going back and forth. Is there anything I can clarify for you?
I'm confused. So I think it's going to take a little bit of time for me to understand that part. But no, you're doing a great job. It's just that I have to probably come back to another class to get it. That's all.
Yeah, definitely. No, it's a lot. It's something that with repetition, it will become easier and you're going to have those aha moments. But yeah, the first time I walked through this, I was like, what is going on here? So yeah, definitely. If you feel a little like this, totally normal. Awesome. So to close us out, closure gives our functions persistent memories between function calls. And closure is part of what makes JavaScript so powerful. It powers functions, helper functions, like once and memoize that help us to keep our code dry, help us to kind of follow that dry principle, because we, again, as programmers, we're not lazy, but we don't want to repeat code. We don't want to be redundant. Do not ask me to repeat myself. I'm going to say it once, I'm going to declare this function once, and that's it. It's a crucial part of iterators and generators. Iterators and generators are very powerful. I encourage you to look those up on MDN and kind of snoop into what those are about. It also powers something called the module pattern, which is a design pattern that we learn about at Codesmith, and that is used across the, the engineering world, that allows us to kind of preserve state or data in an application. In some cases to preserve privacy, in other cases just not to overcrowd or pollute the global memory or global namespace. Also, closure is crucial to the functioning of asynchronous JavaScript. And so much of the web, like the actual practical application, when I go to Facebook or Google or whatever site I'm on, Grubhub, which I'm gonna probably order food after this, asynchronous JavaScript is the majority of the JavaScript happening, and closure is crucial to that. I really encourage you to go to the async JavaScript hard parts. So folks, that is the end of our lecture tonight. Thank you so much